Please join me in welcoming Bob Connelly.
Thank you. Is this on? Oh,
Yes.
Thank you. I need something to remind me of what I want to say. So, well, this all sounds very formal, everything. I have to say, I'd like to tell a little story that happened some years ago when I was visiting Simon, my co-author, who's the chair of the mechanical engineering department at Cambridge, England. And my wife Gail was talking to some of the other women there, and they were talking about bragging about, my husband does this, my husband does that. It's very nice. But anyway, the other woman said, Gail mentioned that I was visiting Simon, who's an engineer. And the other woman said, well, my husband is a pure mathematician. Well, me too. I don't work for Google or anything. I work in the math department. I do pure math. No, I can't help it if it happens to be applied to building things, bridges or whatever. Oh, am I moving around too much? No, that's right. Okay. Anyway, so that's the feeling I have. I'm interested in the subject because of the geometry. I'm not interested in building something because it'll hold up. Because sometimes I build things and they don't hold up. So, and you'll see that later. The question is why things are interesting. Then the question is, how do you show something is rigid? And what do you mean by saying something is rigid? So I think it goes back to one of the first results in this kind of geometry, due to Cauchy, the French mathematician. Maybe you've heard of him if you've taken calculus. What he showed was that if you have a convex polyhedron, so I should explain what that is. Convex means if you have like a polygon in the plane, it means that when you take the polygon and take any 2 points on the boundary of the polygon in the plane, the line segment between them lies inside the polygon. So for instance, my arms, if you can do this, are convex, but this isn't. Convex, not convex. And the same happens for three-dimensional subjects. And what he showed is that if you take the surface of the polygon and chop it up into faces, the flat parts of the polygon, take it apart and reassemble it again so that it's convex, there's only one way of doing it. You could do it so you get the mirror image, but you only get one way of doing it. So what are some examples of convex polygons? Here's one. Here's a regular dodecahedron. This is one example. This is the first non-trivial example is the regular octahedron. It has 8 triangular faces. And here are some others. Well, they're not triangular faces, but this is a nice convex polyhedron. There's a whole bunch of them here. Now, he showed it was safe. Now, if it's not convex, the question was, is it still rigid? So here's one that's not convex. And what do you think? Is this rigid? I claim it is. But how do you tell? The question is, it didn't prove that it was. So I see there was a long theory of this, and it went along, the subject sort of limped along for a while. And there's a sort of natural study of when things are rigid. For instance, in the plane, if you have something like this in the plane, where you have a bunch of points that are connected like this by a rigid bar. In other words, a bar is something that it connects 2 points and keeps them at that same distance. So in the plane, this is rigid, but as it turns out, this flexes into 3 space, something like this. So anyway, in 3 space, and one of the things about prejudice and so on, you know, this woman who talked to my wife has a kind of prejudice for the kind of things that she does, and I have the same sort of prejudice, or some sort of prejudice of that sort. And I just wanted to mention that there was a woman from Germany in the mid-20th century, the first half of the 20th century, Hilda Geringer, who found a condition when frameworks, bar frameworks in the plane, generally were rigid. If you have just the right number to make them rigid, if it's not too over-concentrated on one part versus another, then generally it will be rigid. And later that came to be known as, see if I can remember his name, oh, I'm sorry, I can't remember anything. Lemann's theorem, thank you. It came to be known as Lemann's theorem, where Lemann did the same thing in 1970, and her work was completely forgotten. It's a very sad story. Okay, but anyway, that's just a little sidelight. So, later, it sort of became as a question as to whether all surfaces were rigid. Like this, I think people didn't really believe that this thing was rigid, or it didn't believe it was flexible, but it probably is. And I heard of it through a paper of Hermann Gluck, and people sort of knew, they had results about convex polyhedra and so on, and Hermann Gluck raised the question, or repeated the question, of whether all triangulated surfaces, convex or not, are rigid. And people, every time you build one, or make one, it looks like they are. So I decided I would look at surfaces or triangulated surfaces that were not rigid, and this is one of them. I was very proud of myself. I said, why not take the simplest non-trivial example? This is with 6 vertices, and is it actually rigid? And this is one of them, and it looks like this. It's a little unconvincing about how it does, but because of the restrictions on putting it together. And I proved a more general, a whole bunch of things were like that were rigid, but at surfaces, you can see that this surface, this is a triangulated surface. Here's a square, a rectangle, and here's a triangulation of it, another triangulation of it, and the whole thing flexes up into 3 space, but it intersects. Ugh. Okay. Well, that's fine. I was very proud of this, and then a colleague of mine reminded me that I was a little late in the game. A guy named Raoul Bricard, a French mathematician, proved that this sort of thing was flexible, starting off in the plane, let's say, like this. And we have some other examples of this lying around the world. There are 3 different types. And he did his work in 1896. Sort of, I got anticipated a little bit. But in any case, that was an interesting thing to start. And after I was at IHES, that Henrik mentioned, I was working on trying to get this into a triangulated surface, an embedded surface. It didn't intersect itself. And then I left and I went to Syracuse, taught calculus and statistics. They've never asked me to teach statistics since then. But I realized you can manipulate this a lot. What you can do is you can take on one side, you can take a little triangular pyramid here, and on the other side, here and here. So one side, the triangles reach off on this side, and they reach off on the other side. And you can see the triangular pyramids on each face, they don't contribute anything to the rigidity, and the whole thing flexes, but it still intersects itself. But the two triangular surfaces, the two parts that come together, one of them part goes like this, one piece goes like this, and the other goes the other way. And they start intersecting. Then I had the bright idea of putting two of them, using another version of the triangulated surface to do this, which I call a crinkle. So one goes in here, there's the crinkle, and so this thing starts off flat, but then it opens up, and where the thing was intersecting is gone. So those points of intersection are gone, and that's it, you have an embedded surface. Problem solved. And then Klaus Stefan, who was at IHES the year after we left, simplified this down this way. You can see this, and there are others around. So this is another version of the same thing that flexes. That's it. Now, one of the things about Cauchy's theorem is that Cauchy made a mistake. In 1813, he had, it's something you can see almost every day. Cauchy's theorem relied on this. If you have a convex polygon like this, and you think of it as like a bunch of arms, and in each edge, each corner, you say that the arm opens up or closes up. You'd say it closes like this. You have a convex polygon, and you close it in like this. These two ends, my fingertips get closer together. But his proof was lacking. See, if you go this way, they're further apart. They don't closer to get close, they get further apart. You see, it goes in like this, they get further apart. So my bright idea was to make a model like this. Can you see it? Now, these are chains and these are what I call struts. Don't want to pay any attention to that, but on this thing is rigid. And what happens if you take that arm that Cauchy was talking about, like this, and open it up, these two things get further apart, even if they go funny into three space. And that's enough for Cauchy's theorem. It took them another 50 years to correct what Cauchy did. But this led me to this kind of structure. This is what our Buxter Fuller called a tensegrity. He called it that way after seeing structures like this by Kenneth Snelson. I don't know, if you go to various art museums around the world, you see his structures. This is looking underneath the tower, looking up. He has various bars like this. I call them struts. I'll explain that in a minute. And these things I call cables. The cables can get further apart. They cannot get further apart, and the struts cannot get closer together. So for every pair of points, it's like this. This is a cable. This is perfect cable. You can't pull it further apart, but it does go in. This is a strut. This guy, I have little screw eyes. This is modeled with screw eyes. A strut like this, the two ends can come out. They can come apart. Okay, strut, cable. What's a bar? Can you tell me what a bar is in this lingo? Am I really out of range? What's a bar? It can't change its change, so it is a cable and a strut. Why not? Okay, so this is the kind of thing I think is interesting. Okay, so what I did is I figured out how to tell when these things were rigid. Now, there's a whole bunch of examples around here of things that are rigid. Let me see. This is one. This is what got Kenneth Snelson interested in the subject. This is a tensegrity. Now here I cheated a little bit. I made the cable into a spring. The spring wants to come in. These are true cables. These boys, they don't move an inch. They don't move anything. And these are struts because they can allow it to come out. So this is what Kenneth Snelson made. He realized this thing. Oh, he put triangles on the faces here, but that's okay too. Anyway, so he made all kinds of examples like this, and I realized that there's a theory involved with this, that you can develop how these things are put together and do lots of examples. This Cauchy polygon is one of the nicest. If you have a convex polygon in the plane and you put struts in here, so in the right way, you can be sure the whole thing is rigid. Now, let me see. Well, the next thing I should explain what a stress is. We have stress in all of our modern life, right? Things are pushing on us or pulling on us or something like that. And a stress is just a number associated with each of these struts and cables. The struts have a negative number and the cables have a positive number. And when you take each of these edges and multiply them by that number, you get a force that's in that direction. Add up the forces at each vertex here, these vertices, and you get everything, nothing moves. Everything is in equilibrium. So if you have a stress that's in equilibrium for one of these things, this is a kind of stress energy. What it is you multiply the, you take the sum of the squares of the distances of each of these members times this stress, and you get a stress energy. And that stress energy may have a minimum, or it may not, but if it has a global minimum at 0, if it's a minimum of value, then you have a chance to show that this thing is rigid. And the question is what kind of rigidity you want. Now, what Cauchy showed was essentially what I call local rigidity. It's when the object, you can't move very far. If it's not locally rigid, it flexes, it moves, keeping all the constraints of cables and struts. So if that stress energy is the minimum, that's almost enough to make it rigid. But there's still a few things you have to watch out for. So here's one example. Here's another example of something where the stress energy is just fine. It says the stress energy doesn't change, but this thing keeps moving. What happens is that these edge directions lie on a circle if you move everything to the center. But anyway, this has been known for a long time. This is a ruled surface, a hyperbolic surface, and it looks like this. Okay. Oh, and there's another kind of rigidity with the stress energy. This is one that Bill Baker, an architect, has been playing with. You may have seen some of his work. This is, what do you think? What do you call this? A what? A dream catcher. Yes, but you were, am I too close? There were people, there were little creatures that beat you to this. Well, that's the spider web, exactly. All you have to do is for this thing to be rigid, I'll explain the kind of rigidity, is that the thing is in tension everywhere, positive tension, and these outside things are fixed. It's sort of what got me started. So maybe let me explain the types of rigidity. That is, there's the local rigidity. In other words, there's nothing nearby where you can reassemble it. Global rigidity means there's no way of reassembling the object in the same dimension, like in the plane or in 3-space. In other words, there's only one way of reassembling the object, satisfying all the distance constraints in the plane. And then there's another notion of rigidity where it's rigid in all higher dimensions. In other words, there's no way of, that's what I call universal rigidity, where there's only one way of reassembling the thing in any higher dimension. This thing of Snelson's is just that way, and you can see them around here. Now, one of the things you can do with that is something like this. This is one thing that, it's kind of something that Snelson did, although he cheated. I have to say, he put all kinds of reinforcing cables all over the place. And I think what's special about it is that the struts seem to be suspended in midair, like this. But you can build one things on the other. One interesting idea is that you can superimpose one piece on top of another piece and cancel, if you have a cable and a strut, just think about it. If you have a cable and a strut with the same value but opposite values for the tension and compression, what do you need them for? One, the cable says it can't get smaller, or can't get larger, and the strut says it can't get smaller. So what do you need them for? Throw them away. That's what this does, this sort of thing. It's like that. Okay. But here are some other variations on Tensegrities that you can see. This is, I don't know who, somebody gave this to me, bless their hearts, but this is another thing where the struts are between here and here, but they're sort of in tension with this gadget in the middle. So you can see it goes like that. But it's held in equilibrium, and it's still perfectly, it's universally rigid, whatever. And let's see. This, what do you call it? This Cauchy polygon is just like that. It is universally rigid, like this. That's about all I have to say. These are all variations on it. You can use your imagination and build it. Here's one I did by using this superposition idea of superimposing cables and struts. Do you like it? This is my little man. It's art. Okay. And please have a look around and explain this. Oh, I should mention one last thing. This is a much larger thing where it's using the symmetry of the in space. The way, if you have a regular polytope like this, every vertex is the same as every other. There's a rotation that takes every vertex to any other vertex. Now, these things have to do with certain symmetry groups, and the question is, what do they look like, and how do you construct them? So let me see. I'm going to go. Whoop! I did the wrong thing. There it is. Yeah. So we did a calculation on this kind of structure where every vertex is the same as every other vertex. And we looked at this stress energy function, and it turns out you can break it down into different pieces as part of the stress energy. And so this is the one example of that, where here you can see what it looks like. And depending on the example, there might be a possibility that you can find it so that it will be stress. And you can move it around to see what it looks like. One reason for doing this is to see which struts cross which other ones. Now, one of the favorite symmetry groups is A5. And what you can do is choose how the cables are connected. There are two types of cables. Yeah, let's see. So here's one. Yeah, hang on. There it is. Notice that there's a pentagram in there. See the pentagram, the 5-pointed star? It turns out that when you have that, you can do a superposition of another kind of pentagram and cancel the stresses on the inside. Wait a minute. No, it's the other way around. Well, anyway, there's another version of this where the pentagram is replaced by a pentagon, and they're related by this superposition property. And then you can do it. Now, let's see here. We can do this. You can change the shape by changing where the points are, like this. There's sort of one parameter of motions that you can change. Now that's something like this one. If you, forgive me, I'm going over here. This, again, I thought the pentagrams were nicer than the pentagons. It's not a given that every time you have a pentagram you can find a pentagon or conversely. But in this case it happens that you can do it. And this is one of the ones, if I could find it, it would take me a while to find it in the software. But this is in there. So this has the property that the struts are fairly close to the surface, and the cables represent the outside of the surface. So there are two pardon me? Oh, sure, I can do that. So it's like this. It's heavy. It looks like this, if you can see. And I guarantee this is universally rigid. It's in Cauchy, in the polyhedra, sometimes what you can do is you can take some of the face and punch it in so that it goes from a realization in a convex realization to one that's not convex, where one of the things inside are equivalent. So it's not rigid, it's not globally rigid in 3 space, but this baby, I claim, is universally rigid, even in dimension 64. It's rigid everywhere. In other words, there's no other realization anywhere in any high dimension. There's no other flex in any higher dimension. The poor thing is getting soft, safe. So that's stiffness, which is another thing I'm going to say. Anyway, so lastly, I'll show what these things, oh, I've gone on the wrong one. Let's see, no, it's this. Is it this one? No. Oh. Okay, I think when you get into the convex thing here, there it is. Then you do this. There's me, Simon, and this is part of I think it's something very similar to this one. One of these ball Tensegrities that I claim is universally rigid. An engineer would say, it's not really rigid. You push a little force, you can't resolve the force pushing on the outside. That's true, but this thing is universally, you can't really reassemble it anywhere, even in a higher dimension, where the cable and strut constraints are satisfied. Anyway, so there are a lot of examples, and you can see them around here, of various kinds of Tensegrities. There are groups of people who really believe in the Tensegrity principle that these things are useful in some sense. And as I said in the beginning, I don't care. I just think they're interesting, all in their own. Okay, that's it. Thank you. Yeah, if you have questions.
I tell my Thurston Sullivan story.
What's that?
Do you mind if I tell my Thurston Sullivan story?
Yeah, well, go ahead.
Back in about 1976, when Bob was giving a talk at a really major math conference. I was in the very back row, and in the second to last and last row also were two of the really great topologists of the 20th century. And the younger one, Bill Thurston, who for a while was on our faculty, was playing Lunar Lander on his phone. This tells you how far back it was. And so Dennis reached his foot forward and kicked Bill in the butt and said, "Pay attention, Bill, this is the oldest theorem, oldest conjecture you're ever going to see proved." Now, Bill went on to be awarded a Fields Medal, which is the equivalent of a Nobel Prize in mathematics.
No, it's better.
Anyway, I will never forget that little moment.
Yes, in the back.
This is probably outside the box, but at the corner of 140 New York City, corner of 140 Broadway
Yes.
and the street, there's a solid dodecahedron. So when I look at that, what should I think about with respect to mathematics?
It's a regular dodecahedron?
It claims to be by the sign.
Is that what this is? That's icosahedron. Okay, I forgot. The dual is the dodecahedron. That's right. Right. That's in this symmetry group at the A5 at the very end of my little program. And you could rigidify. What happens is that some of the points are sort of in special position. And so the kind of things that I'm doing, usually there's 60 points instead of whatever points. How many points are there? 20 for the regular dodecahedron, something like that. Yeah. So the symmetry is the same as these. But if you want to reinforce it and make it into a tensegrity ball, then you might look at, the first step would be looking at my little software here. You could turn it into a rigid dodecahedron, rigid tensegrity. That's what I think. That's the way I think about it.
Well, there are also some questions from Zoom.
Pardon me?
So we switch up between the Zoom questions.
Oh, we have another question back there.
Okay.
Just briefly, yeah.
I'm just curious about some of the steps that you involve improving rigidity.
Yes.
There's one hint about the local minimum stress energy.
Right.
What else?
But this
In
is,
terms of a global.
well, yeah, well, that's another thing we talk about. You should read the book. Okay, so that's one of the things that you can do. The unusual thing about the progress in the book, this is a global property, very global, very unusual when you have an energy function like this. But any kind of energy function can be broken down into this kind of stress energy, and then there's a kind of infinitesimal energy, which is more local than the thing. Now, an engineer might look at this and say, this is pre-stress stable, so what do you want? Well, yes, it is, but it's more. Yeah. Oh, yes, okay, I forgot. Yes, more. Yes, somebody on Zoom.
Yes. So the first question is, I have to move back up because we have a few right now. Can we hear more about prejudice in geometry or against geometry?
Well, but like most people, I like to talk about my prejudice. And the Hilda Geringer was a very interesting, she had it, this was in the 1920s, maybe 1919, 1930, something like that, where she did this work. She did 2 or 3 papers on this subject, which were really right on the mark. And then the other person, what's his name? Leman did this in 1970, and it was much later. Laszlo Lovász got into the act also, and he showed why there was, in that case, an algorithm for proving a very fast algorithm for proving what's called generic rigidity. This is sort of relying on Geringer's theorem, but that's another story. That's the local theory, which I also learned from a group of people in Montreal at the time. Henry Crépeau, if you are into matroid theory, and Jaros Baraks, an engineer from Hungary who went to Montreal, and especially Walter Whiteley, that they had a very nice independent theory that goes back to I have trouble remembering all this stuff. Who's the famous mathematician in the 19th century? Pardon me? No, the famous physicist in the 19th century. What's that?
Maxwell, yes.
Maxwell, yeah. The Maxwell-Cremona theory, which was a very nice, pretty result relating polyhedra in the plane with stresses to lifts of the polyhedra in dimension 3. So it's a way that engineers use to understand the stress, the equilibrium stress on three-dimensional, let's say, bar frameworks. And that sort of was overlooked and so on. I'm sorry, I'm not talking too much. I don't know too much about Hilda Geringer, but that was just recently discovered in the last 10 or 15 years. It's really interesting. Anyway, she was German. She had two things she had to suffer from. One, that she was German in the time of the Nazi era, and that she was a woman. It made it, I think that both contributed to her not being noticed, in my opinion. Any more questions?
Definitely on Zoom.
Let's say if you have a group, let's say A5,
Mm-hmm.
then you know there are 60 vertices, and based on, you probably also know where to place those 60 vertices based on some kind of geometry. But how do you determine where to place cables and struts between those? Because for 60 vertices, you can place.
Well, that's sort of
roughly
determined
60
beforehand. So what happens is that there's two subgroups. One subgroup depends on each of the K, as you see in the picture here. Right. There's the purple group. That corresponds to a little subgroup where each element is of order 5. Each element goes to another element of order 5. And the other one is a subgroup of order 3, where each element returns to itself after 3 times. And the struts I like are the ones that the struts are completely disjoint, that they don't intersect each other. Like, well, this isn't in A5, but like this. This is why,
Back to the microphone, please.
pardon me, yeah, this is why, what's his name, I can't remember anything. The architect who made this, this is why he liked them. I think a lot of people who build the Tensegrities, the novelty of it is that the struts are held suspended by cables. Unfortunately, I didn't bring all the possible models I could have, but there are tables where the upper part of the table is sort of suspended by cables to the bottom one, and yet the upper part never touches the bottom one with the strut. So with this thing, to answer Albert's question, the thing is you decide on the geometry of the connections beforehand. That's it. And it has to be symmetries. It has to have the whole symmetry. So the group acts on everything in some way, and you choose a way of acting the way these things act, so that this is the arrangement. So this is the arrangement, but it's not given that the thing will be universally rigid in dimension 3. What happens is I hate to get technical, but there are various representations of the group A5. One is there are 2 in dimension 3, 1 in dimension 4, and 1 in dimension 5. And they, in a sense, compete against each other. If the 3-dimensional representation, or one of them, wins in the battle for dominance in the tensegrity, in the stress matrix, then that's the one that gives you the picture. There are many of these examples in this software where you can see you don't get any good picture. And that's probably because one of the higher dimensional representations are winning in the stress energy battle, if you want to put it that way. I hope I understand what I'm talking about. Yes. Some of you had, you were going to heckle me.
I wondered about the word prejudice in the title. Are you talking about aesthetic prejudice?
Yes.
What did you mean by prejudice?
Well, it's this, I think of myself as a pure mathematician, as pure as anything you can imagine. And it's true, I'm very happy to learn from engineers. The lowest of the low. And I'm very happy to have something might apply to engineering as well.
Engineering faculty to your talk, and that consists.
It's my prejudice, yes.
Yeah,
And Hilda Geringer's prejudice is another kind of prejudice. I think we all have that sort of prejudice.
preference.
And it's sort of how we operate. We have to operate that way.
I have a question from Zoom. Are kids being taught about Tensegrities, do you know?
Well, there's a group of people, I invited them to come on Zoom, who like to build these things. And there are various techniques. My technique is kind of, I've seen other people, we had a little meeting earlier this year, actually during COVID, with a bunch of us Tensegrity types. And my technique is to use these brass tubes as struts and actual cables as cables. And some of the other people in this group have done the same thing. I'm not original in that way. But I think you can. It's not bad. Now, there are other methods. I don't have any here. One way is to take a wooden stick and put something like a screw eye, something at the end of the wooden stick. The trouble is it hurts the wood. And then put a rubber band as cables between the vertices. And that's a perfectly good, easy method to do it. What happens is that when you do that, it comes to its stable shape. Now, that shape often is universally rigid, but not necessarily. It might just be locally rigid in dimension 3, which is fine. So local rigidity is perfectly good. In fact, there is a very nice theorem of what's his name? Boy, I get all fussed up. Ben Roth and Walter Whiteley, that says that if you have something that is locally rigid for an engineer, I don't want to explain that, but it's this kind of thing that will absorb forces as a bar framework, and then there's a stress that's on the whole thing, a proper stress, it's an equilibrium, then you can replace the cables, replace the bars with that have a positive stress with the cable, and the bars that have a negative stress with the strut. And it's locally rigid as the bar framework was. Which is, I was kind of jealous when they proved that. Gee, wow, I didn't think that. That's so simple. It's a kind of duality theorem. And that's another thing, but that's local. My deal is universal. Dominate the world. Yes, in the back.
So the previous question was, are kids learning about Tensegrities? And I'm a math undergrad and I had never heard of them. And so I'm curious how you arrived at this field
Well, part of it was through this group in Montreal with Janusz Baraks, an engineer, Walter Whiteley, and Henry Crépeau. Henry Crépeau was, I'd say, the most mathy of all of them, and Janusz Baraks was an engineer. And they introduced me to the subject as a mathematical subject. And I thought it was very interesting. This is when I was, before I was fired here at Cornell.
I didn't mention them. Yeah. There's another question. Is Bob ever planning to return to the Fields Institute in Toronto to conduct another Tensegrity?
Yes, I am. There is going to be a conference this summer, next year. And I hope I put in an application and I hope to go. It's a little difficult to travel these days, COVID and age and all that sort of stuff. Yes. Yes, we're very friendly to the Fields Institute. They've been very good. Yeah. Let's say, I think there is a conference and I think it's going to be, there's the question is going on. I also talked to some of the people at IHES in France too, and they were very nice. I don't know when or if I would go there, but I think that would be, we loved our time in France, even though we were poor. Yeah. Yes.
This is not exactly on the topic of the talk, but it's something that I think shines through in the way you presented the talk, which is, not sure what to call it, something like intellectual integrity, or following what turns you on personally, as opposed to what might be fashionable or considered mainstream or something like that. Do you have any comments about like how to choose an area that excites one, or whether it's dangerous to be outside the mainstream or anything like that?
Well, as a personal history, yes, when I got I have another story to tell. When I was a graduate student at the University of Michigan in Ann Arbor, Frank Raymond introduced me. You know, somebody sat down with the beginning grad students and so on. I think what they were doing, the reason I was there is because they were in need of large numbers of TAs. In any case, he taught me, well, what do you want to do, Bob, when you're here? And I said, I want to do geometry. And he says, oh, we don't do that here. How about topology? That's close enough. And so I did. And I sort of wasn't comfortable. I don't know why. It didn't fit. It wasn't, the problems were getting too hard. There was sort of, it's like the problems that we give students in calculus, where there's a lot of calculation and stuff. And at the end, you get the right answer. I'm like, oh, that's hard. It's not that I was just intellectually curious. I couldn't do it for some reason. It's a handicap. I have to do what I can do.
But I mean, it looks like you have a lot of energy to make things and to try things and.
Yeah, energy is not the problem, I think. It's the interest and feedback and so on. Yeah, I have a lot of energy. I play a lot of Go online too. It's a lot of energy. But I keep getting weaker. Yeah, Jim.
I'll quote from a letter of recommendation from back then. Absolutely the best problem solver at the university. And that includes Mort Brown, who is a famous topologist, who prided himself on his problem-solving abilities.
I took a course from Mort Brown, and that was great fun. I enjoyed it. He gave up after a while and did the Moore method, where you give problems to the students and let them work on it. They're not allowed to go online. There was no online when he was up. And you are also a student of R.L. Moore, right? Or no, a student of R.L. Moore. Right, and I'm a little one generation before that. It sort of was, people were trained to solve problems. They were given a way of doing things with just solving problems.
But the point is that he's an original.
So I'd like to, I don't think I'm particularly quick, but I like problems. And I've had students like that too, that I don't think they're terribly quick to solve a problem, but they're insistent on trying to solve the problem, which I think makes up for a lack of speed.
I am reminded of A Beautiful Mind passage in that about Nash and the way he absolutely obsessed on a problem that he didn't know anything about, but eventually solved it. It's one of the really famous math results. And he seemed to have that mindset.
Oh, I also forgot to mention, one of the things that I think about the book. How do you read a book? How do I read a book? I don't read very well. For one reason, just tell me how to do, give me a problem, I'll try to work on it. But I think for our book, I would hope, I don't know if you can do this, especially for students, there are a few here. I would hope what you would do is open the book and look at the pictures. Exactly, look at the pictures. I hate that some math books pride themselves on not having a picture in it. That's crazy. Look at the pictures and see what it does. Then if something interests you, read something about it. And then do it. And certainly read the parts that you're interested in. You don't want to just begin in the beginning and work your way through and say, oh, I'm stuck, I don't understand that. I did that once for a book on electricity. I worked my way through, I got halfway through and I got stuck on one part, I never made it through that one part. That's not the way I like to read a book. I don't know about you. I like to look at a book, if I look at a book, and look at the pieces that are interesting. Yeah, it's true, I like to say, give me a problem in the book and I'll work on it. That's true, that's what I like to do. I'm not sure, maybe I'm not a very good reader, maybe eyes are bad, I don't know.
Well, we are at time.
Yes, thank you for your questions.